Hoover High AP Chemistry. This is part 3 of the answers video for day 69. Weak acids and bases. This is the last assignment before the Christmas winter break. We have a couple more problems to finish up. Again, remember you will have an over the break assignment coming, about 6 to 8 hours on two separate subjects, two new subjects rather, and please have that done before you come back on Monday, January the 4th. All right, but we'll finish this up today, and you should be able to finish this assignment on Friday. Okay, so here we go. We have another weak acid reaction with hydrofluoric acid, and we're going to deal with 2.63 molar solution. I did not give the Ka on the sheet, so here it is right there. It's 6.6 times 10 to the negative 4. Now, if you were an enterprising person and you saw this and saw that I hadn't given you a Ka, you simply could have gone online and looked for it and found the Ka. It's just a very common number. It's very easy to find if you just type in Ka for HF in Google. It'll bring that up right away on the first page, what that value is right there. Okay, so let's go ahead and do this. Let's write this reaction out. So HF. It's not one of the strong acids. It kind of looks like a strong acid, but it is not a strong acid. It is a weak acid. And there's the conjugate base of hydrofluoric acid. And it produces hydronium ions, which is the characteristic of an acid. That's what an acid does. Okay, so fill in the rest of the table. So this is the initial concentration. We never include water. We assume no initial concentrations over here if they're not given. Every coefficient here is a 1, so it's going to be minus 1x plus x. These are increasing. They start at 0. They can only go up. Okay, and then just do your subtractions and additions, and it looks like every other problem we've done on this assignment. Okay, we'll write the law of mass action. And HF goes over here, goes on the bottom. Okay, there that is. And now we're going to substitute in the algebraic values and the Ka value. Okay, there that is. Now we're going to use the simplifying assumption, and maybe you're gaining some experience that if you look at that and you know it's below probably -3 or less, so -3, -4, -5 on down, that it's probably safe to use the simplifying assumption. The one problem we had earlier with -2 there, it wasn't a valid assumption. You couldn't get rid of it. That number, this number was just too big, and so that means the x value is going to be too big. It means more of the solution is going to break off over here, and you're going to have a bigger x if this number is bigger, but it's small enough that we're probably safe. So let's go ahead and get rid of that x right there, and so we have this. Okay, now we're ready to simplify, multiply both sides. Okay, and then we're going to multiply these two together. Okay, I'm going to just switch sides on everything, and we're going to take the square root of x squared. You don't need to adjust the decimal here because you're not at a final answer yet. Okay, so the square root of x squared gives us x, and the square root, that is a 1 there. Square root of 17.36. And we get this. Okay, so that's the x value is, and again, it should be, I made this error earlier, it should be 0.042. Okay, so that is going to be the hydronium concentration, the value of X. Okay, so we can write that here. That's one of the questions it's asking. And that's molar. All right, so the second thing it's asking is pH. And again, use your acid-base roadmap. You have this, that's the dot. You're moving over to this, so it's negative log of the H3O concentration. And that gives us a pH of 1.37. Okay, so that answers everything that it's asking for hydrofluoric acid at that concentration. All right, now we're going to do a problem with the same concentration of hydrofluoric acid, but this is a common ion reaction problem with the common ion effect. What we're going to do is before we put this in the solution, we're going to put some potassium fluoride in the solution first at this concentration. All right, now let's look at what that does. Now, just to keep the concept separate, we're going to put this in first, and then we're going to put this in second. But in actuality, it doesn't matter what order you put these in, because that's the whole point of equilibrium. A solution will reach an equilibrium no matter what you start with and what you finish with, or which side of the equation you start with and finish with. It always ends up at the same place at the very end. That's the concept of an equilibrium. But just to keep the concept clean, we're going to put the potassium fluoride in. So we put in 1.1 molar potassium fluoride. And so what I'm going to do is I'm going to write a mini rice table just for the potassium fluoride. Okay, and I'm going to write it in abbreviated form, okay, which we usually don't do, but I'm going to do that here. So over here is my mini rice table. So it's KF, and this is going to act like a strong acid or base. It's not an acid or base. It doesn't have a hydrogen on it, a hydronium on it, but it acts in a way like the rice table did for hydrochloric acid. So we start off with this. It's a one-way reaction, because potassium, if you look at your solubility rules, potassium on your solubility rules, potassium's right there. It's soluble with everything. It's going to totally break up with everything that it's with. In this case, it's with fluorine, and so it's going to totally break up with that. So KF is going to go to K plus and F minus. Okay, so we're starting off with 1.1 molar. So let's just write it. This is RI. Again, this is how you can just write a rice table. It doesn't have to be complicated and have all kinds of squares there. Just write it like that. So this is going to be 1.1. And over here you start off with 0 here and 0 here. Now the change, again, we can get into X's, but we don't need to. If it's going to totally dissociate, that means the change is going to be negative 1.1. This is going to completely break up. We don't really need to do the X's, and that should be a 1. Okay, so 1.1 minus 1.1. At the end, you're not going to have any of this, in other words. It's totally dissociated into what's over here. Over here, you're going to add 1.1 molar. That's going to give you 1.1 at the equilibrium. It's not an equilibrium, really. It's just a complete reaction. And over here, same thing. It's a one-way reaction. It goes all the way to this. Okay, so just as with the concept of hydrochloric acid, a strong acid, we start off with all reactant, and we end up with no reactant. We start off with no product, and we end up with all product. So just the simple shortcut is, however, whatever the concentration was of this compound that will totally dissociate, that's going to be how much we end up in equilibrium with the K plus and the F minus. Okay, so what does that mean? It means this. We don't care about the K+. It dissociates with anything it's with. It's not going to recombine with anything. F- could recombine, but it's not that we're concerned about that. All we want to know is how much are we starting with. We put this in the solution before we put this in. Again, that's not important, but we're going to say it's important just to keep the two reactions separate. So we put this in first, it totally dissociated, and it gave us 1.1 molar of fluoride ions right there, okay? So now we're ready to start this reaction, the same reaction we did in the last problem, except the difference is we're going to start with a fluoride concentration really over here. So let's go ahead and write the reaction, this HF reaction again. Okay, and now we're ready to fill in. So we have 2.63 molar of HF. We don't do anything with water. We don't start off with any H3O+. This hasn't reacted yet. But here's where the difference is. Instead of this being 0 as it was in the last problem, we're going to start off with 1.1 molar that came from the potassium fluoride. Okay, so notice what ion came out of potassium fluoride. It was F-. What ion is going to come out of HF? It's F-. That's called a common ion. Let's try to think about in advance then what's going to happen to this reaction. We had the same reaction before, except we had no F-. Le Chatelier's principle says if we reached a certain equilibrium with this, and we started the last reaction with no F-, okay, and we reached a certain equilibrium of F-, which was X, which is the same as we had for hydronium, 0.042. If we start off with F- already in the solution, we're going to push the reaction back to the left. It reaches a certain equilibrium with this much fluoride, but if we already have fluoride in the solution, it's going to say, hey, I've got too much fluoride. I started off with some already, so it's going to want to move the reaction back to the left, and it's going to want to create HF. Or another way of looking at it, it's not going to let this HF break apart as easily because there's already too many F- ions in the solution. So this is not going to want to break apart as easily. Therefore, the solution will be less acidic. It will produce less. It won't go to the right. It won't produce hydronium ions. And that's what the common ion effect does. So what we should expect to find in our second reaction, this reaction, is a higher pH, fewer hydronium ions, fewer of these, and a higher pH, which means fewer of these, which means a less acidic solution, okay? So I did kind of a graphic of this in the instruction video, so go review that as to how this kind of flows. I did it with a different compound. All right, so let's go ahead. Again, all the coefficients are 1, so this is going to be minus X, plus X, and plus X. So this is 2.63 minus X. 0 plus X is X. And now we have an initial concentration, so it's not X here anymore. It's 1.1 plus X. Okay, so you see this difference in this problem is over here in this column. So again, the solution's already got a bunch of this in here. So when the reaction flows from left to right, it creates this. But if there's already a lot of this in the solution, or some of it in the solution, the reaction won't be able to flow from left to right. It's going to say, hey, I've already got too much fluoride, too much F-, so I need to go backwards. And so this won't break up, therefore this won't form, and the solution will be less acidic. Okay, so that's the concept of a common ion effect with this particular reaction. It can have other effects as well. All right, let's go ahead, write law of mass action. And now we're going to plug in our numbers. We have the same Ka value. It's still hydrofluoric acid. Okay, H3O is going to be X. F minus fluoride is going to be 1.1 plus X. And that's all going to be over 2.63 minus X. All right. Now we can make our simplifying assumption. Again, it worked last time. You know, I didn't calculate it last time. That's okay. It would have worked. Okay, we would have been below 5%. Okay, but it's a small number, so it should work. So that means we're going to get rid of this X right here and this X right here. So that means the reaction is going to look like this. Okay, this is the reaction without those X's right there. I have the X and the 1.1 and the 2.63. There it is right there. So again, we're just going to do the math down here. Same number we got on the last problem. That didn't change. This is what's changed over here. So now we're going to divide both sides by 1.1. Come over here to do that. So I'm dividing this by 1.1, so I'm going to end up with X equals. Okay, so there's the X value. And that's the hydronium concentration. So let's come on down here. And made a mistake. No, I didn't make a mistake. Yeah, let's show a difference between this. Remember, we normally had an X squared situation. It didn't happen here because you had X times 1.1 plus X. But you could get rid of this X. So the X didn't exist over here anymore. It's just 1.1 times X. So that's why we didn't end up with our usual X squared. Instead of X times X, it was X times 1.1 in this case. So you don't have the X squared situation, so you don't need to do the square root. Okay? Okay, so this is the hydronium. I'm going to write it down here. This is asking a different question. I'm going to go ahead and write it down here. This question is related to what we're doing. And I'm going to adjust the decimal now since it's a final answer. Instead of 15.78, it's 1.578 times 10. Okay, we went from 15.78 to 1.578. So we made this number smaller, so we have to make the exponent bigger. Bigger is in the direction of -3. Okay, 1.578 times 10 to the -3 molar. Now we're going to figure out the pH. The pH is equal to -log of the hydronium concentration. And all of that is over here on the acid-base roadmap. You're going from here to here, so it's -log of hydronium concentration. And so that's going to be and that gives us a pH of 2.8. Okay, so let's do a comparison now of the pH back here on the previous problem where it was just HF into pure water, same concentration into pure water. What we ended up with was a pH of 1.37. So let's go ahead and I'm going to answer this question. Compare the pH of the previous two reactions. Explain why the second reaction has a lower H3O concentration and a higher pH. Let's just focus on the pH. Higher pH means lower H3O concentration, and it's an easier number to work with. So let's just focus on that. So here we go. So we have pH, and in parentheses I'll put HF in pure water. and that was 1.37. That's on the previous problem. Okay, then we have pH, HF in common ion. You already had some of that fluoride in there. And that came out to be this, 2.8. So the higher pH means lower H3O concentration, less acidic. And this is higher H3O, higher than this. It's more acidic if it's a lower pH. So again, why did that happen? Okay, it wants you to explain that. So the existence of fluoride in the solution created an imbalance. And Le Chatelier's principle says if you have an equilibrium situation and then you increase the concentration of products, it's going to move backwards. It wants fewer products. It's out of balance. So it's going to move backwards. Moving backwards means less of this is going to dissociate. In fact, just the opposite. You're going to have this reassociate with hydroniums and form HF again. You're going to increase your concentration of HF. Okay, that means you're going to decrease your concentration of hydronium ions because the reaction is moving to the left. So let's kind of write that out as an explanation, because that's a lot of what the AP is writing explanations, okay? Okay, I'll leave it right there at that. So, the presence of the common ion in solution, when you put the potassium fluoride in and it totally dissociated, you started off the reaction, the hydrofluoric acid reaction, with some F- already in solution on the product side. Okay, again, it's over on this side. Instead of the first reaction we did where there was none, now there is some there. So this is throwing the equation, the equilibrium, out of balance. It has too much on the product side. So the reaction is going to move backwards in this direction. That means it's going to not only not make this, it's going to actually reduce the concentration of this, of the hydronium ions. And that means less acidic solution. Less acidic solution means higher pH. Higher on the pH scale is less acidic. All right, so the presence of a common ion in solution, F- on the product side, means that the reaction, RxN's abbreviation for reaction, is out of equilibrium and favors reactants, meaning it's going to go back to the left. This causes less hydrofluoric acid to dissociate and less H3O+ to be formed. This produces a less acidic solution and a higher pH, so we ended up in this last reaction with pH of 2.8. In the first reaction, the pH was 1.37. It was lower. That means more acidic. So that's what the common ion effect does. It affects the equilibrium and therefore causes the reaction not to move forward as easily as it would. Okay, I think that's enough. There's a couple of problems on the last page. They're not terribly important, and I am going to leave those maybe for another time. They're just not an important concept. So that's it. That takes care of all the assignment before the break. So get this done. Try to get this done this week. I know the solutions are a little late getting up, but you have time to do this and grab this, get this done. And then look for the Christmas winter break assignment coming out maybe in the next few days to a week, okay? I don't expect anybody to work on it in the first week. It'll be to you by the second week, and I'll notify you that it's been up. Please get that done over the break, and because it's a concept we're not going to have time to do in class. And have all of this done. Be sure you know acids and bases pretty well coming into class after the break. Buffers are going to be kind of a little more advanced treatment of acids and bases, and you need to have these rice tables down pretty firmly. Okay, so that's it. Have a wonderful Merry Christmas, Happy New Year, whatever you celebrate. Enjoy it and be with family and enjoy them. And I wish you the best. Please feel free to contact me anytime over the break, and I'll be happy to help you or tutor you or help you deal with grade situations, whatever you need. Okay, so have a wonderful holiday. Bye-bye.